Hello everyone, welcome back to this online class. So today we are going to look at something on orthogonal trajectories, and the question is how to find the orthogonal trajectories on the surface of the sphere. We are told x squared plus y squared plus z squared is equals to 9 of its intersections with the paraboloids xy is equals to k times z, where k is a parameter or a constant. So to be able to work out this question, what we're going to do, we say let f of x, y, z be equal to x squared plus y squared plus z squared minus 9. Remember, usually the surface is f is equals to 0. So that's why we are subtracting 9 so that we have 0 on the right hand side. So let f be equal to that, and g of x, y, z be equal to xy over z. We are dividing by z because usually g is always a constant. So g must be equal to a constant k, or whichever constant. So you make k the subject so that you get x, y over z. So now that we know f and g, we need to find their first partial derivatives. So let's start by differentiating f with respect to x, y, and z respectively. So the first partial derivative, so you can say therefore, partial f with respect to x, which can be written as f subscript x. So when you differentiate with respect to x, you assume that y and z are constant. And so that will give you 2x. Partial f with respect to y, that will give us 2y. Partial f with respect to z, that will give us 2z. So those are the first partial derivatives of f. Let's do the same to g. Partial g with respect to x, that will give us y over z. Partial derivative of g with respect to y, that will give us x over z. And partial derivative of g with respect to z, that should give us negative xy over z squared. Remember, when you're evaluating partial derivatives with respect to one of the variables, you assume that the other variables are constants. And that's what we have done to be able to find these partial derivatives of f and g. Now we need to find the direction cosines. Direction cosines at point x, y, z. So you can write direction cosines of f and g at point x, y, z. So how do we find them? The first one is P capital, which is defined by or defined as the Jacobian of fg with respect to y, z. This can be written in terms of determinant as the determinant of partial f, partial y, partial f, partial z, partial g, partial y, partial g, partial z. That is determinant of 2 by 2 matrix. Let us replace the partial derivatives. F with respect to y, we got 2y. F with respect to z, that was 2z. G with respect to y was x over z. And g with respect to z was negative xy over z squared. So when you multiply, of course, the leading diagonal, you multiply this, then subtract the product of the minor diagonal. So when you multiply this, you're going to get, of course, we start 2y times negative xy over z squared. That will give us negative. Let me start by writing the negative. So that will give us negative, that is a negative 2x y squared over z squared, then minus the other product of the other diagonal, that is 2z times x over z, that is simply 2x. 2x. Let's find the other direction cosine, the Q capital. This is defined as the Jacobian of FG with respect to zx. In terms of determinant, this is written as determinant of f, partial z, partial f, partial x, that's the first row. The second row is partial g, partial z, then partial g, partial x. And we have these partial derivatives. Let us substitute f with respect to z, that is 2z, f with respect to x, that is 2x, g with respect to z is negative xy over z squared, and g with respect to x is y over z. So again, determinant of that 2 by 2 matrix. Let's evaluate that determinant. We start by multiplying the elements along the leading diagonal. Then we are going to subtract the product of the elements in the other diagonal. So that will give us, leading diagonal, when you multiply, that will give us 2y. Then minus, remember this will be a minus and a minus. I can see this, that minus, instead of writing minus twice, this will just be a plus. So that will be plus 2x squared, 2x squared y over z squared. Another direction cosine is r capital, or capital R. This is defined as the Jacobian of fg with respect to x, y, and this can be written as determinant of partial f, partial x, partial f, partial y, partial g, partial x, partial g, partial y. So that determinant, remember, when we talk of partial derivatives, we will also use the subscript notation. When we say partial f with respect to x, that's the same as f subscript x, etc. So in some books, you'll find most of them using the subscript notation for partial derivatives. So let's replace these partial derivatives. Partial f with respect to x, that was 2x. F with respect to y, that is 2y. G with respect to x, that was y over z. And g with respect to y was x over z. If we multiply, we start with the leading diagonal, then the other one. So when you multiply, leading diagonal will give us 2x squared over z, then minus the other product, that will be 2y squared over z. Now, we also need to get other, we call them other direction cosines, of course, for the orthogonal family. Remember, when you talk of orthogonal trajectories, you're given a family, and your task is to find another family of curves such that every curve in the first family will intersect with every curve in the second family, at 90 degrees or at right angles. So for us to be able to solve or simply find the ODE corresponding to the orthogonal family, we need to find the other direction cosines, which we are calling, I'm going to use a different color to differentiate them. So we'll call it P prime. How is it defined? As the determinant of partial f, partial y, and then partial f, partial z. Then here we have q, and here we have r. That's how we define it. And we have these partial derivatives. So let us replace f with respect to y, that was 2y. F with respect to z, that is 2z. Then we replace the value of q. Let me check. We got 2y plus, that was 2y plus 2x squared y over z squared. That is q. Then r is the same as 2x squared over z minus 2y squared over z. So let us work out that determinant. I'll start by multiplying this, then the other product. So when you multiply, this is what you're going to get. Well, let's start with the leading diagonal. We are going to get 2y times 2x squared z. That should give us 4 yx squared over z minus 4 y cubed over z. Then subtract the product of the other diagonal, that is minus 4 yz. Remember it is a minus, so another minus 4 x squared yz over z squared. So anything that will cancel out, so this can also be written as, you see, this minus 4yz minus 4x squared yz over z. So this you can simplify. Look at this other one. This z will cancel with one of the z, so that we have negative 4x squared y over z. And we have here positive 4x squared y over z. So we expect that the whole of this term will cancel with this. And so we can now simplify. This is the same as, let me write in a proper manner, negative 4 y cubed over z minus 4y z. And you see, I can see 4y is common. 4y is common. So this you can as well write as, because negative 4y is common, so negative 4y. That one you factor out, so that or simply I could factor out negative 4, so that I don't interfere with the others. Let's factor out negative 4. So what do we remain with? I'm going to write it. When you factor out negative 4, we'll now have y cubed over z plus y z. So that is p prime. Do the same to q prime. Q prime is defined as the determinant of partial f, partial z, partial f, partial x. So here we have r, here we have p. So that's determinant of that 2 by 2 matrix. Let's replace those partial derivatives. F with respect to z, that is 2z. f with respect to x, that is 2x. What did we get as r? That was 2x squared over z minus 2y squared over z. Then our p capital, let me check. We got negative 2xy squared over z squared. This is what we got. Negative 2xy squared over z squared. Then I can see there is another term, minus 2x. So minus 2x. Determinant. So we multiply, we start by multiplying this, then the other one. So when you multiply, leading diagonal, we'll get negative 4x y squared z over z squared minus 4xz. Then the other diagonal is now negative 4x cubed. Negative 4x cubed over z. A minus and a minus, that will be plus. So plus 4x 4x y squared over z. Look at our first term. This z will cancel with one of the z, so that we have negative 4x y squared over z. And also the last term is positive 4x y squared over z. So those two will cancel. The whole of this term will cancel with this. So we remain with negative 4xz minus 4x cubed over z. Negative 4 is common, so this you can write as negative 4, factor out negative 4, so that we have xz plus x cubed over z. So that is our q prime. Then the last one is r prime. So let me take this up. So the last one is r prime. This is defined by the determinant of partial f, partial x, then partial f, partial y. Here we have p, q. Let me substitute the values. So f with respect to x, that is 2x. F with respect to y is 2y. Our p, let us replace our p capital. Of course, we have it. You can read it from here. That was negative 2 xy squared over z squared minus 2x. That's our p. Our q, what was it? That was 2y plus 2x squared y, 2x squared y over z squared. So that determinant, again we multiply, this will multiply this, and the whole of this will multiply to y. So let's start with the product of the leading diagonal. Product of the leading diagonal, what are we going to get? If we multiply, we are going to get 4xy plus 4x cubed y over z squared. Then now the product of the other diagonal, a minus and a minus will be a plus. So this, we expect this to be a plus now. 4xy cubed, 4xy cubed over z squared, then plus 4xy. So is there anything that will cancel? I can see 4xy, that's twice, so that will give us 8xy. So let me simplify that. But you can also see that xy is common. So you see, if I factor out 4xy, I am going to get 1 plus x squared over z squared, then plus y squared over z squared plus 1. 1 plus 1 will give you 2. If I factor out the z squared, this can also be written as, and let me pick another color, 4xy over z squared in bracket x squared plus y squared. Remember, I'm factoring out z squared, so this will be plus 2z squared. It's the same thing. The same thing. So now we have found those direction cosines. So what is the equation that we need to solve? So you can say therefore the ODE for the orthogonal family, for the orthogonal trajectories, is given by, so for you to get the orthogonal trajectories, you must solve this ODE, what we call ODE for the orthogonal trajectories. It is given by dx over p prime equals to dy over q prime equals to dz over r prime. Let's substitute those primes. So you can say or dx, our p prime, we got -4 into y cubed over z plus yz equal to dy over q prime again was -4 times x cubed over z plus xz. And this should be equal to dz. Our r prime we have just found 4xy over z squared times x squared plus y squared plus 2z squared. So we need to solve this equation. Now we can simplify. Look at -4. This cancel with that, so that here, or simply let's cancel the 4. We return the negatives. So this thing can as well be written as dx over -y cubed divided by z, then minus yz. This should be equal to dy over -x cubed over z minus xz. This should also be equal to, I want to open the bracket, or I can just leave it the way it is, dz over, let me open the bracket. This will give us x cubed y over z squared. The other term will give us xy cubed over z squared, so plus x y cubed over z squared. And the other one is plus 2xy. So that's what we get. Now let's solve this. What we need are just 2 unique solutions. I know you can find more than 2, but we are only interested in 2 unique solutions. And remember, when it comes to orthogonal trajectories, the given family f is equals to 0 will be one of the solutions that you're looking for. So in case number 1, f is equals to 0 is necessarily one of the solutions or one of the integral curves. One of the integral curves. F is equal to 0. What was it? We are saying, i.e., that x squared plus y squared plus z squared minus 9 is equals to 0 is one of the solutions. I can rewrite this as x squared plus y squared plus z squared is equals to 9. That is one of the orthogonal trajectories. One of the solutions of this equation, the one that we have up here. So you remain to find the second solution. And the easiest way to find the second solution is to use the first solution to eliminate one of the variables in the equations that you will pick. So in case 2, I want to pick the first two fractions. We're going to say dx over negative y cubed over z minus yz. This should be equal to dy over negative x cubed over z minus xz. But you see negative is common. So this we can divide by negative so that we have dx over y cubed over z plus yz equals to dy over x cubed over z plus xz. I've gotten rid of the negative. So I want to eliminate z because you see I've picked dx and dy. So you need to get rid of z between these two equations. So let's rewrite. In the first equation, you see this equation is separable. If you look at it, it is separable. This equation can as well be written as if I cross multiply, I'm going to get x cubed plus xz over z dx. But before I separate the variables, there's something I want us to look at. Let me just wrap what I've written here. You see, we cannot separate, and yet we have the z variable. So I can multiply both numerator and denominator by z, so that the equation can as well be written as z dx over y cubed plus yz squared is equals to z dy over x cubed plus xz squared. And you see this z will cancel with the other z. So we have dx over y cubed plus yz squared is equals to dy over x cubed plus xz squared. Replace z squared, use your first solution. Instead of z squared, so we write put or substitute z squared is equals to 9 minus x squared minus y squared. What are we going to get? We are going to get this. Let me write it. We're going to get dx over y cubed plus y into 9 minus x squared minus y squared. This should be equal to dy over x cubed plus x into 9 minus x squared minus y, of which if I open the brackets in the denominators, let's see what you're going to get. This will give us or dx over y cubed minus, these are plus 9y minus x squared y minus y cubed. This should be equal to dy over x cubed plus 9x minus x cubed minus xy. So y cubed will cancel with this y cubed. Again, x cubed will cancel with this. So this will give us dx over 9y minus x squared y. This should be equal to dy over 9x minus, remember here, there was xy squared, this is a square, let me add it, xy squared, the last term, because you're multiplying. So that's 9x minus xy squared. So look at the denominators again. Something is common in each of those denominators. So you can write or dx over, I can see y is common, so that here we have 9 minus x squared. This should be equal to dy. I can see x is common, 9 minus y squared. Now you can separate the variables, or x dx over 9 minus x squared is equals to y dy over 9 minus y squared. This is now separable, ODE, which you can now integrate directly. If I introduce an integral here, another integral here, you're going to use U substitution. In the first one, in the first integral, you're going to let u to be equal to 9 minus x squared, so that du is equals to negative 2x dx, or x dx is du, which means x dx should be equal to du over negative 2. In the other integral, the right hand side, you're going to let v be equal to 9 minus y squared. That means dv is equals to negative 2y dy, or where we have y dy should be equal to dv over negative 2. So when you make these substitutions, what will we get finally? We are going to get this. This integral will now give us the integral of, remember now, it will be 1 over u times du over negative 2 is equals to the integral of 1 over v times dv over negative 2. The negative 2 will cancel out. It's like now we are just talking of the integral of 1 over u du is equals to the integral of 1 over v dv, of which if you integrate, we are going to get ln u equal to ln v plus ln c2. And if you get rid of the logs, if you apply the laws of logarithms, you're going to get u over v is equals to c2, which means what was our u? Our u was 9 minus x squared. Our v was 9 minus y squared, and that is equals to C2. So we have found the second integral curve, the one that I've circled, bracketed. So look at that one in case, the answer in case 2, and the answer in case 1. Let me take this one. This is what we got in case 1. And what we have found in case 2 is this one. So those that I have ticked are the orthogonal trajectories. They are the required orthogonal trajectories. Of course, you can find a third one. Check if you can be able to find a third one. It is possible. But I told you, once you have found the first two, then there's no need of finding another one. But you can just check that case 3. Try to use this x dx minus y dy. When you do that, the denominator will be x squared minus y squared. You simplify. That should be equal to z dz over 4, not 4, but that should be 4, yes, over 4 plus z squared. Should it be 4? No, it's 9, not 4. So this should be 9. You check this. This will, when you integrate this, you're going to get the third integral curve. The answer, when you work it out, you need to get your other integral curve should be x squared minus y squared over 9 plus z squared is equals to C3. Any two integral curves are okay. So this is how to be able to find orthogonal trajectories of any given family of curves. So thank you all for watching. Please subscribe to my YouTube channel. That is Professor Francis Okech. Just go to the YouTube search and type Professor Francis Okech. Now, when we meet next time, we look at other problems in partial differential equations. Bye-bye.